So here we are, histidine and serine. We've got a little bit of a problem, but we've got a little bit of a solution also. That histidine residue, that's the state that we want it to be in order to turn over a new, or basically to begin catalyzing this reaction again. Serine, on the other hand, no, we can't really work with that. Serine is still covalently linked to our substrate. We've got to get rid of that. Well, how are we going to do this? There's going to be some growing pains. There's going to be some emotional strife, absolutely, but we can handle it. We've got H2O. We've got a nitrogen on a histidine ring that has a lone pair of electrons. That lone pair of electrons is going to go pick up one of those hydrogens. And what that's going to mean is that the electrons that connect our oxygen to our hydrogen on our water molecule are going to swing down to that carbonyl carbon. Whenever they swing down to that carbonyl carbon, that's going to cause one of these bonds to swing out to the oxygen. Now, whenever all of that happens, when those electrons are pushed around, what we're going to end up with is something that looks a little bit like this. Erase all this, redraw it. And, oh, we're all right. We're going to have a negatively charged oxygen. We're going to have a nitrogen to hydrogen with a positive charge there. Then we're going to have an OH. Okay. Now, this right here should stand out as like, okay, well, that's a little bit off because histidine, that's positively charged. We wanted it to have no charge. We wanted it to have a nice lone pair of electrons. Serine, we're still covalently linked. Not a problem though. The electrons that connect our serine residue our uh, to our carbon, they can swing over here and pick up that hydrogen, giving these electrons the opportunity to swing back to that positively charged nitrogen to give us a negative charge there. In addition to that, these electrons right here on my single bonded oxygen can swing back to give us something that looks like this. Now, all of that taking place, what we're going to lead to is something that looks like this whenever I redraw it all. Well, let's revisit each amino acid. Histidine, well, got deprotonated. So histidine, when it's deprotonated, has a lone pair of electrons. I'm going to draw those in green. Okay. Now, serine, well, it went and picked up that hydrogen from our acidic or our positively charged histidine residue. So which electrons were those? Those are the ones that I have depicted in blue. So that's gone. Okay, so serine's back to how it wants to be. Now, the only thing that's left is reconciling or dealing with or redrawing these carbon to oxygen bonds or this carbon to oxygen bond. And we got something that looks a little bit like that. And that's it. That's the end of our covalent catalysis for for a serine protease. Now, some of these parts might seem a little bit funky and different rendering than maybe you've seen before, but basically this is everything that's happening. Now, serine proteases are a large class of enzymes that they vary based on what's their substrate? What's the substrate that they seek out? There are some that in the second position here, they would want to see a positively charged residue or a negatively charged residue. Highly variable class of enzymes, but they are basically all going to follow this same sort of catalytic mechanism. All right, well, I hope that was helpful, and I hope you have a good one.